Hello guys, I hope you all are doing good. I am Vaishali Kikan and we are discussing the optical communication. Today in this video, we are going to talk about the rise time budget analysis. We had already seen the power budget analysis and point-to-point link in the previous video. I hope you all have seen that video. If not, it is highly recommended that you go back, watch it first and then come to this video. Today we are going to focus upon the rise time analysis. Why do we require to analyze the time for a given circuit? We require to analyze the time for a given circuit so that we can have an idea about the bandwidth. And when we know the bandwidth, we can guess what is the speed over which the circuit is going to operate. So now for the system designing, I need to know what is the rise time analysis. With the help of the timing budget, I can design the system. Right, in the power budget, I told you how much power was sent to the receiver from the transmitter. So PR and PT were known and we knew what was the noise margin. How much power we need to require for transmission from transmitter to the receiver and how much power is required for the receiver to operate. And this is how we calculate what is the power we have to give to the transmitter, so that it can compensate the power losses in the channel and it can also compensate the losses which are occurring at the receiver, and the receiver will be responding actively towards this input. Right? So this was the power budget analysis. In the similar manner, if I want to design the system, I will be having the rise time budget analysis as well. Right? So it determines the dispersion limitation of the given fiber link. How much dispersion would be there in the fiber and how much dispersion is going to cause the attenuation problem and the power loss problem and the bandwidth problem in the given system. The dispersion is going to mainly affect the bandwidth. Right? So we are going to see what all elements are there which are going to provide the dispersion. We are going to mathematically justify them, and after that we will be going to see what is the system time that is required. Right? So we have to design our system over this time only. If I design this system below this time, there would be not sufficient on-off time gap and our information will not be provided sufficiently from the transmitter to the receiver. Right? So we need to understand the rise time analysis. So the rise time degradation is found to be some root of rise time of each contributor. From each element we are going to see what is the rise time. I hope you remember what was the rise time. Rise time was the time required to rise for a given optical signal from 10% to 90% of its value. Right? So from 10%, the 90% value increment for the output is going to give me the rise time. So we are going to talk about the rise time of the different elements. We are going to have their square and we are going to add up them and then we are going to take the under root square. So now the under root is going to give me the T system, or T system can be represented as summation T is equal to I to N Tri square under root. Right? So this is how I can represent this equation. So pulse rise time degradation is found using the root sum of rise time of each contributor element. Right? If I want the switching in the source as well as the detector, the switching in the source as well as detector should be as fast as possible. Right? I want the fastest switching, and what I want, the dispersion should be lowest enough. So when it would be happening, I would be having the fastest switching and the lowest dispersion when I am working upon this T system. Right? So T system is a very important parameter which is going to give me the switching rate as well as the dispersion which is happening inside the fiber. Right? So the bandwidth requirement which is for a given application, it should be developed and it should be found out by developing the rise time budget analysis. For a particular application, we will be finding out the adequate bandwidth after only finding out the rise time budget for this application. And for that we should understand how we are calculating the rise time for each element. So the sources and detector, the light sources that we have or the detectors that we have are both having their finite response time, right? Because they are taking some time to turn on or off. The sources or detector are not turning on and off instantaneously. So I require the finite response time. Again, it becomes essential to find out what is the response time. So the resultant bandwidth, because it is not turning off also instantaneously, so the resultant bandwidth is determined by rise time as well as the fall time. We should understand what is the rise time, what is the fall time. By having analysis of both of them, we can determine the resultant bandwidth. And here you must understand whatever joints we have. We have the splices, we have the connectors, we will be having the couplers in the circuit. So these are not contributing to the rise time budget analysis. Instead, they are going to contribute in the power budget analysis. We had seen that in the previous video. So they were responsible to change the power, but they are not changing the dispersion inside the fiber. We are assuming this, right? So what are the basic elements upon which my rise time budget analysis will be dependent upon? So we are having 4 basic elements. The first element is a transmitter rise time, which is represented as T, Tx. Then we have the group velocity dispersion rise time, which is represented as T, GVD. And then we have the modal dispersion rise time, which is represented as T mod, MOD. And then we have the receiver rise time, which is represented as TRX. So first of all, we have the transmitter rise time. So the transmitter rise time is represented as TRX, which is known to the designers, right? So it is contributed by the light sources and its circuitry. So we know what kind of light sources we are using. Either we can use the LEDs or we can use the lasers. So depending upon the light source, that is LED or lasers, we will be having the different transmitter rise time, right? So they are known to the designer. If he is using the LED, he will be having the different rise time. If he will be using the lasers, he will be having the different rise time. So rise time, there is no mathematical formula. It is known to the designer. Right, after that we have the group velocity dispersion rise time, TGVD, right? So obviously it is going to cause because of the dispersion. So here, because of the group velocity is there, we have the group delay dispersion, right? We have different modes. Due to the different modes, we will be having the group delay dispersion, and it is measured as TGVD is equal to DL sigma x. So now where D is the dispersion of the fiber, it depends upon the length of the fiber as well. So it depends upon L, which is the length of the optical fiber. After that, it is dependent upon sigma lambda, which is a half power spectral width of the source. So again, it depends upon what kind of source I am using. If I am using LEDs or if I am using lasers, I will be having different TGVD, right? Obviously, because LED will be having more number of modes, and lasers, because we know it is not having much of modes, it is coherent, so it is going to have less number of modes. So half power spectral width will depends upon the type of the source. Again, it depends that what kind of source I have used in the circuit, LED or laser. Then we have the modal dispersion rise time. Modal dispersion rise time is represented as T mod, and it is given by 440 upon Bm. Right, so now here Bm is the bandwidth of the optical link of the length L, right? So after that, the receiver rise time. The last parameter is the receiver rise time. So now here the receiver rise time is calculated as the time taken by photodetector to respond to the 3 dB electrical bandwidth, right? So if I have 3 dB bandwidth, and we will be finding out the photodetector response for this 3 dB bandwidth, I will be finding out the receiver rise time. So receiver rise time is represented as TRX is equal to 350 upon BRX. right? Again, BRX is the bandwidth of the receiver, right? So here I have talked about 4 type of elements: the transmitter rise time, the GVD rise time, the group velocity dispersion rise time, the modal rise time, and the receiver rise time. All of them are rise times. So we can calculate their fall time as well, right? So we can calculate both of their times, rise time as well as fall time. So this is the analysis which is done for the rise time. So the total system rise time will be found out using this formula. I told you whatever elements we are having, we are going to take their rise time, we are going to square them, and we are going to add them and then take the under root. So we are going to take all of the elements TTX, TGVD, T mod and TRX. We are going to square them: TTX square, TGVD square, T mod square, TRX square, and then we are going to take under root, right? So T system is going to be equal to TTX. So because TTX is already known, we are going to take its square. Now TGVD was D L sigma, so its square would be D square L square sigma lambda square. Now T mod was 440 upon Bm, so its square would be 440 upon Bm square. So these are added, is added to TRX, which is 350 upon BRX square. So we have taken the under root, and this is how we can find out the T system, which is going to tell me what is the rise time budget for the initial system design. So for the system designing, rise time budget analysis becomes really important. So I hope you understood each one of the things that I have discussed in this video. If you have any doubt regarding any of the topic that I have discussed, you can put the doubt in the comment and I will be trying to resolve your doubt as soon as possible. I hope you like this session. If you like it, please push the like button, subscribe to the channel, share it with your friends, and also give me your feedback. Thank you so much.